Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ukobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 4. It says a hot air balloon is rising at constant velocity. So note that keyword there. They say at constant velocity. When a tourist leans over the edge and accidentally drops the camera. When the camera lands on the ground, it bounces once and then comes to rest. They say the velocity versus time sketch graph below depicts the entire motion of the camera from the instant it is released until it comes to rest on the ground. They say air resistance has been neglected. Then, okay, we can see our graph here. Looking at the fact that we can see that this velocity versus time graph is a decreasing function, we know that they took upward as positive. So let's note that so that we know that our acceleration has to be substituted as negative 9.8 meters per second. Now 4.1, they say a camera while falling is regarded as a projectile. Explain what is meant by the term projectile, right? So let's just quickly run to that. So what is a projectile? We say a projectile is an object that has been given an initial velocity and moves under the influence of the gravitational force only, right? Okay, now we are given 4.2. It says write down the velocity at which the balloon is ascending from when the camera drops, right? We want the velocity in which the balloon is ascending when the camera drops. But then we do know from the previous question that we were dealing with a hot air balloon case, we know this, right? We know that the velocity of the hot air balloon will just be equal to the initial velocity of the projectile, which in this case is the camera. So the initial velocity of the camera will be the same velocity of the hot air balloon, which we do know to get the initial velocity, we usually look at the y-intercept, right? So the y-intercept there at the beginning indicates our initial velocity. Remember that the graph here is showing us the motion of what? Of the camera, right? So that means that the initial velocity of the camera is 16 meters per second, which means the hot air balloon is also moving at a constant velocity of 16 meters per second. So we want to indicate that and say this is 16 meters per second. In which direction? Upwards, right? Then, okay, 4.2.2 says, write down the time for which the camera is in contact with the ground before bouncing, right? Now, this is what you need to indicate to understand, meant to say. So this is what you need to understand. This is the initial velocity here, and this is the time. Remember what happens. This is a hot air balloon. From that situation, we knew that this is a hot air balloon and the camera drops. The camera just does not just drop like this. It has to go up first, and then it comes to the ground. So it goes up, follows the direction of the hot air balloon until it realizes that it's no longer inside the hot air balloon. Then it changes the direction and goes down, right? So if we can just break this down into segments and say, let's separate here. So basically what we have in segment number 1 is when the camera jumps up to the maximum height, which corresponds to that. And then when it comes back from the maximum height all the way to the ground, let's say this is segment number 2, the whole of this, right? So this will be indicated by this part on the graph. So this is when it jumps up to the maximum height and then reaches a velocity of 0. From the maximum height, it now goes back to the ground, which means it's increasing its velocity and hits the ground, strikes the ground at this point. So it strikes the ground at a velocity of what? Negative 64.56 meters per second, right? But then here, what happens? After striking the ground, it stays in the ground for some time, right? Because this is an inelastic collision. It stays in the ground for some time, and then that's the contact time with the ground. And then after that, it bounces off the ground. Bounces off the ground at a velocity of what? 8 meters per second. So this distance here, or this part here, indicates when it stays in the ground, when it's in contact with the ground, which is what we are looking for, the time for which the camera is in contact with the ground before bouncing off the ground. So how are we going to get that? Obviously, we must get that by subtracting these two values. So if you say 8.62 minus the 8.22, you will get 0.4 seconds, which will represent the contact time with the ground. Right. So I hope that makes sense. Now, 4.3.1, they say now they want the value of x shown in the graph. Now, the value of x is when it bounces off the ground and it goes where? After bouncing off the ground, we know that it goes upward and then reaches where? The maximum height. So we know that it's going upward because the velocity is decreasing all the way up until it reaches the maximum height where the velocity is supposed to be 0. So now, in other words, we are looking for the time it takes to move from the ground, to bounce off the ground to the maximum height. So how can we get that? Obviously, there will be no need for any calculations, deeper calculations, because this is only 2 marks. So we need to be really smart about this. If we can just predict or show the trajectory of the camera, we say the camera moves up a bit and then comes back to the ground, stays on the ground for a while, bounces up to a maximum height, which is point X, and then comes back. Now, what we have created here is a perfectly symmetrical graph, right? This is a parabola graph and it's perfectly symmetrical, which means that the time it takes to bounce off the ground all the way to the maximum height will be the same time it takes from the maximum height back to the ground, right? So the time that we are looking for is this, but then we are indicated, we are given the time in which it leaves the ground, bounces off the ground, and the time in which it comes back again to the ground, whereby it comes to rest. Okay, so now if we can use the fact that this is symmetrical, we can find point X here by calculating the midpoint of these 2 points here. So simply by saying, let's just subtract in between here to find the time it takes, right, to move from this point, to bounce off from the ground all the way to the maximum height and back to the same ground. Let's find the time it takes. And then how can we do that? We can start by saying, let's take the, what's this, 10.26. Let's take the 10.26 and subtract the 8.62, right? So in your calculator, you will say 10.26 minus 8.62, right? And then you get what? 1.64. So when you get 1.64 here, what you must do is you must realize that this is the time from here to here. That's 1.64 seconds, right? But then you are looking for the value of X. You are looking for the value of X here. So which means what must you do? This is perfectly symmetrical. The distance from here to here is the same distance from here to there. So that means divided by 2. 1.64 divided by 2. So this is going to give us what? So this is going to give us 0.82 seconds. Right, now we have 0.82 seconds. But then we're not going to write 0.82 seconds for X. Now note that we do understand that 0.82 seconds is only just the time it takes from here to here. That's 0.82 seconds. But then to indicate the value X, because this is a progression of numbers here, right? So we can't have 0.84 here while we have 8.62. So what must we do in order to find the value of X? So we must say 8.62 plus the 0.82 that we are seeing there. And then when we add those ones, we will get what? We will get 9.44 seconds, right? So that means the value of X there is 9.44 seconds. And that's just basically how you were supposed to tackle that question right there. Okay, pretty nice one. Then we move to 4.3.2. It says height of the balloon above the ground when the camera is dropped, right? When the camera is dropped. Now, obviously, we don't know the height in which the hot air balloon is at the moment when the camera is dropped, right? And the only information that we know about the hot air balloon is its acceleration of 0 meters per second and its initial velocity of 16 meters per second. So we don't have pretty much in order for us to calculate. And also the fact that we do not know the time it took for it to move from the ground all the way up there. Remember, the time that we are given here is only for the camera, right? But then we can use the information of the camera in order to calculate that, right? By assuming that if the camera is dropped here, let's just assume that the hot air balloon is just stationary at that point. And then now the camera is being dropped. And then if it's dropped, it goes all the way to the ground, right? Now we can calculate the displacement of the camera, which if you can check here, the displacement of the camera will be indicated by the distance from the ground to the hot air balloon. So if we find this displacement from the ground to the hot air balloon, we have found the height of the balloon above the ground, which is what we are looking for. So we will use the camera to say the V initial of the camera is 16 meters per second. Now we said they took upward as positive, so our acceleration is negative 9.8 meters per second square. But then we can see the final velocity of the camera here. VF is equals to negative 64.56 meters per second. And what else do we have? We have the time it takes to reach the ground. Delta T is equals to what? 8.22 seconds. And then what are we looking for? We are looking for the height, delta Y, right? So we can choose any formula with delta Y. And then we can just go with the straightforward formula, which is delta Y is equals to V initially plus V finally over 2, and then multiply that with delta T. Now, what's our V initially? 16. What's our V finally? That's the negative 64.56, and then all that divided by 2. And then multiply that by what? By 8.22, which is the time, right? Now you're simply just going to grab your calculator and punch all of that. So we have bracket 16 minus the 64.56, and then divided by 2, and then bracket multiply that by the 8.22. Right. And then when you punch that into your calculator, you get a negative 199.58 meters. So I'm just going to round off to 2 decimal places. Right. Negative 199.58 meters. And that becomes the height of the hot air balloon. So we'll then conclude and say a height of hot air balloon above the ground is what? Is 199.58 meters, right? So we do understand why it becomes negative. It becomes negative because we took upward as positive. So we took up as positive, therefore anything that we calculate and is going downward, it will appear as a negative value. Right. So we have that. So we simply used the information of the camera to find out the displacement of the camera. We know that this part here will cancel out because the distance it takes moving to the maximum height and coming back to the initial position in which the camera was dropped or in which it fell, then it's the same. So the part here, the displacement over this part is just 0, meaning the displacement will now be left to be the distance in between the hot air balloon and the ground. Okay, so now we are fine with that. 4.3.3 says, calculate the maximum height that the camera reaches after it has bounced. So, okay, let's come back here. Remember, we said here, this is when it bounces off the ground. When it bounces off the ground, where is it going? It is going to the maximum height, which is at point X. Now, we already know that the time it took from here, from bouncing off the ground to the maximum height, is 0.82 seconds. So again, we can use the information of the camera at that point to say that the V initially of the camera when it bounces off the ground is 8 meters per second. But then what is the time it takes to reach the maximum height after its first bounce? It's what? 0.82 seconds. And then the final velocity when it reaches the maximum height, we know that at the maximum height, the velocity is what? 0. So 0 meters per second. They took up as positive, so our acceleration is negative 9.8 meters per second square. Then we are looking for our delta y. Now, any formula with delta y would work here. So we're just going to go again with the simplest one, delta y. Okay, let me just change the formula just for the fun of it. A delta t square. Then vi, that's 8. Our delta t, 0.82. And then plus half. Our acceleration is what? Negative 9.8. And then delta t is 0.82 and then square that, right? So you're just going to punch all of that into your calculator. And then when you punch it into your calculator, it gives you what? It gives you 3.2. Okay, so let's check. 8 multiplied by 0.82 plus half multiplied by negative 9.8 multiplied by 0.82, and then you square that, right? So this is giving us 3.26527, which we can take it as 3.27, rounding off to 2 decimal places, right? So obviously, if you use other formulas, maybe there might be a difference in terms of your decimals. So, but then should be round about there. So 3.27 meters. And then, okay, let's now proceed. We have 4.3.4. It says, calculate the distance between the camera and the hot air balloon at time x. We already know the height of the camera at point x. So this is height at point x. Height at point x of camera. Right. So there is no need to recalculate that. We already have that. So we're just going to indicate this is 4.3.3. And then for 4.3.4, that means we can only just calculate the height of the hot air balloon at that particular point. So to calculate the height of the hot air balloon, we're simply just going to do this, right? We can say at this point, what is the time here? We calculated and we found that it's 9.44 seconds. So we want to know the time that the height that was covered by the hot air balloon, right? During that time interval for 9.44 seconds. So we can calculate that mainly by saying for the hot air balloon, this is what we have. We are going to say, do we have the V initial of the hot air balloon? Yes, 16 meters per second, right? And then, do we have the acceleration? That's 0 meters per second square. And then, do we have the delta time? Yes, that's 9.44 seconds. And then what's the final velocity? Because it's moving at the constant speed or constant velocity, still going to be the same. But then we are looking for delta y, right? So any formula with delta y would work. And then let's just go with delta y is equals to vi delta t plus half a delta t square. Now our initial velocity, that's 16. And then our delta t, that's 9.44. Then plus half, our acceleration is 0. Then the time is 9.44. Note that we are putting 0 because this is for the hot air balloon. Now, all of this will just give us 0 here. So that means we can just punch 16 multiplied by 9.44, which is supposed to give us 151.04. So this is 151.04 meters, right? So this is the height that will be covered by the hot air balloon at that point. So, okay, in order to then calculate now, this is what we are going to do. So note this. Note this. I want you to just note this. Remember, the 151.04 that we have calculated there is the height of the hot air balloon from that position it's in, right? Not from the ground. So from that position it was in when the camera dropped above the ground. So that's 151.04 meters. But then remember, already we had calculated that hot air balloon was already how many meters above the ground? We did calculate in what? In 4.3.2, that this was at a height of 199.58 meters above the ground. So above the ground, it was 199.58 meters above the ground. And then from that point, remember, as the camera drops, this is still moving upward. It is rising at a constant velocity upward. So that means the whole distance now after 9.44 seconds above the ground will be you having to take this plus that. So to find the whole height above the ground at 9.44 seconds at point X, you are going to say 151.04 plus the 199.58. So I need you to understand that. So this was the hot air balloon at the moment when the camera dropped. But then remember, as the camera is coming down here, what is happening to the hot air balloon? It's rising up at a constant velocity. By the time this is on the ground, right? By the time this is now on the ground and then bounces up and then also reaching a maximum height, this is still moving up, right? So it bounces up, reaches a maximum height. And then at that point X, we find that this is already at a height of what? That plus that. So plus 199.58. And then now we find that it is at a height of 350.62 meters above the ground, right? So that's the one part that you need to understand. Now that we've found that, what are we going to do? We are going to say we have calculated that the height of point X when it bounces here, when it bounces off the ground, it reaches only a height of what? 3.27 meters. Meaning if we want to find the distance between the hot air balloon and the camera at that point, it's just going to be the distance from here all the way up there, which, how are we going to find it? We're just going to take all of this minus that, right? So to find this portion here is just all of this minus that. So our conclusion here is that our height, the distance between, so the distance apart, so our conclusion is that the distance apart will be this. The distance apart the camera and the hot air balloon will be 350.62 meters minus the 3.27 meters, which is going to give us what? So you grab your calculator again, 350.62 minus 3.27 meters. And then we find that it's 347.35 meters. 35 meters. There you go. Right. So that was a very, very interesting question right there. Had a lot of components in it, but then you just needed to take your time in understanding that question and having to come up with the correct answers right there. Right. So that's how you were supposed to go about that question right there. Okay, nice. Now, 4.4 says sketch a corresponding position versus time graph, showing all of this, right? For the entire motion of the camera, they want you to indicate the values of the following. So the values that we must indicate is the height of the balloon when the camera is dropped, maximum height that the camera reaches after bouncing, the time when the camera strikes the ground for the first time, the time when the camera leaves the ground during bouncing, and the total time taken for the camera to come to rest, right? So obviously, this is what we want to start by doing. So there, we are drawing a position versus time graph, and then we are taking the ground as the reference, right? So as the 0 level. So this is the ground here. And then basically I said it is very simple to draw a position versus time because you just simply mimic the trajectory of the projectile, right? So your time in seconds. And then what happened? The camera being released or being dropped from that hot air balloon, it starts by following in the direction of the hot air balloon before it comes back down. So it follows, reaches a maximum height, comes back down to the ground, and then stays in the ground for a while, contact time with the ground there, and then bounces up to a lower maximum height, and then comes back to rest. Okay, so what was the height here? We did calculate. Remember, everything that we'll just be putting in here are the values that we already calculated. So we had what? 199. So we had 199.56 here. And then at this point, we had what? At this point, we can see that it's the 8.22. And then here, it's the 8.62. And then right here, that's the 10.26. And then what was the height that was reached after the bounce? That's 3.27 meters, right? Okay, so basically that's just that. So we've indicated everything. The height of the balloon when the camera is dropped. So there we go. That was it. And then what was the height? They say maximum height that the camera reaches after bouncing. There we go. And then time when the camera strikes the ground for the first time. There we go. Time when the camera leaves the ground during bouncing. There we go. And then the total time taken for the camera to come to rest. There we go. So, yep, that would exactly be 5 marks. And then you can just say position versus time here. So, yep, that's how we were supposed to have this. So make sure that you come back to the video, watch it as many times as possible, and just try to understand the approach that I took into solving all these questions here. But then with all that being said, see you on the next episode. Ciao.